Alright guys, welcome back. We're going to finish up our discussion here on the continuity equation. We're not going to do any application yet, but we're going to kind of go a little bit deeper into some stuff that we weren't able to go into before, such as mobility and recombination inside a semiconductor. But this is where we left off last time. We derived the continuity equation for electrons and holes in a semiconductor from Gauss's law and Ampere's law. And using the divergence theorem. So did a little review from electromagnetics, and now we're back to semiconductor physics. And if you can see from these equations, you know, a couple of general things. I mean, it's a pretty, it looks pretty complicated, and it's because it is. You know, it's this is a second order multivariable, you know, differential equation, a partial differential equation. You know, you have, you know, equation. You know, if you were to, you know, solve this, you know, using several boundary conditions and you know, using some techniques used for partial differential equations, you would end up getting, you know, for P, you would end up getting a function of T and X, right? And it would be very, very complicated. And you know, in physics, in semiconductor physics and electrical engineering, we try to avoid, you know, solving long partial differential equations. But if we know how to apply boundary conditions and initial conditions, we can, you know, simplify these a lot. And we can just look, you know, by looking at this, you know, and for a lot of situations, like let's say if we have a uniformly doped semiconductor, well, that means that there's no doping gradient. So, you know, terms like this right here, you know, this term right here, you know, are all going to go to zero, right? And if it's uniformly doped and it's not hooked up to anything, then there's no electric field. So this term's going to go to zero too, right? And all we're going to have is a generation or recombination. And if we assume it's at steady state, which means nothing is changing over time, well, then we can get rid of this thing, you know, and then we have a simple equation of just our generation is equal to our recombination, right? And you know, what is generation? Generation occurs when electron-hole pairs are created by some sort of outside mechanism, some kind of outside force. And you know, the most commonly would be, you know, when we have light, when we shine light, you know, some photon with energy hv, which must be greater than or equal to the band gap. You know, here's our band gap right here. It's going to create these electron-hole pairs, right? And of course, silicon is an indirect band gap semiconductor, which means there's this delta K right here that it has to overcome. You know, and this could come in from phonon scattering, but needless to say, you know, direct transitions from the valence band to the conduction band for electron-hole pairs is very, very low probability in indirect band gap semiconductors such as silicon and germanium. However, we're going to get into the fact that in silicon and other elementary semiconductors, there are these impurities such as gold. Gold is, I think, the most common, and gold has this energy level that's about you know, halfway up the band gap from the valence band, right? So electron-hole pairs, electrons can be created by creating an electron-hole pair in this mid-gap and in this valence band, and then it can go from the mid-gap to the conduction band. So it's kind of an intermediate band. I don't know what the correct term is, but yeah, this intermediate metastable, I think, is a good word for it. You know, it's where the electron will exist here for a short time and then transition up here, or you know, it'll you know, come down and get trapped here in this, and then eventually come down there and get trapped down there in the valence band. So, but we're gonna talk about generation. So generation has to be some outside force. Recombination is something that happens inside the semiconductor. You know, and these equations really only apply to something called minority carriers. You know, and minority carriers are, well, they are exactly what they say they are. You know, if I have an N-type semiconductor, you know, with some, you know, Fermi level up here, right? And a hole is created, you know, I get a hole, you know, by some kind of generation or whatever, you know, then this hole, the hole H plus is a minority carrier inside an N-type semiconductor. Similarly, with a P-type semiconductor, an electron is the minority carrier in that, and that's really what the continuity equation applies to. So I can actually kind of rewrite these by introducing a subscript N, meaning this is the hole in an N-type semiconductor, right? N, right? And this would be P, right? and P and P, just like that, right? So, so now we're going to talk about mobility a little bit. We didn't get a chance to talk about this before. This will be a really general discussion, and then we'll go back to what we call Schottky-Hall-Reed recombination. So mobility, which is mu, for a hole it's mu sub p. For an electron it's mu sub e. And mobility in general is equal to this this ratio, charge times tau, which is our relaxation time, over the effective mass, m star. And this tau is actually a weighted average relaxation time due to several different scattering mechanisms that occur in a semiconductor. Right? We apply an electric field to a semiconductor. It has some force equals negative E times electric field, right, inside a semiconductor. And furthermore, we apply this electric field, and we get this force acts on the electron in the semiconductor, and the electron drifts with some drift velocity mu sub n e. So I'm just talking about electrons right now, but all this will apply to holes too. The only difference is the signs change and a few other things. But so this mobility here really determines how easily this electron moves through the lattice. Right? And this is really how electrons move. They go like this. Right? Here's your electric field. Right? You apply an electric field to a semiconductor, or maybe this is a built-in electric field from a p-n junction, or from a depletion region, or from any kind of graded doping. Right? You get some kind of electric field, or it's applied. It doesn't matter. Right? So naturally, the electron is going to drift to the right. Correct? Opposite direction as that, but it doesn't go like this. Instead, it goes like this. Right? So in general, the electron is following this direction by some drift velocity v sub d, but it's not going in a straight line. It's encountering these different types of scattering mechanisms inside the semiconductor, and it's slowing down and speeding up again, slowing down and speeding up again. And what we call the distance, like say here's a collision, and they go straight, and then here's another collision, right? The distance, or the time, the in between one collision and the other is called tau, right? The correct term is the relaxation time, right? And so if you think about it, if we have a large relaxation time, a large average, weighted average relaxation time, then we're going to have very good mobility. But what does that mean? That means that there's going to be less scattering mechanisms. So what are those different scattering mechanisms in a semiconductor? Well, there's a lot. There's phonon scattering, one of the most important, or one of the most prevalent. And photon scattering is actually divided up into 3 or 4 different types of scattering mechanism. There's a acoustic phonon scattering, right? There is optical phonon scattering. And there is polar optical phonon scattering. Okay. In addition to that, there's also ionized impurity scattering. Right? So this is if you have doping, if you have an intrinsic semiconductor, this isn't a problem, right? There are no ionized impurity scatterings, ideally, but there always is some impurities, that are probably probably a few of them are ionized, right? But if you think about something that's very highly doped, you're going to have a lot of ionized impurities, and so your mobility is going to be lower. The other one is one that's a little less prevalent. We're not going to really talk about it, but it should be mentioned, is carrier-carrier scattering. Okay? So, 2 electrons traveling through, and if they're close enough together, the wave functions overlap, and it's going to cause some, another scattering mechanism, right? And then finally, we have piezoelectric scattering. This is not something you're going to see so much in silicon or any elementary type semiconductor, because it really the piezoelectric effect really has more to do with when you have two different atoms, and the electronegativity is relatively high between the two. Gallium arsenide, indium phosphide, gallium nitride. The electronegativity between the anion and the cation, or the group 3 and the group 5 atoms, is going to lead to this piezoelectric effect, and that's going to affect it. But really, the main two we're going to. Oh, and there's also another one, and that's neutral impurity atoms, or defects, and that's pretty important too. That's actually a little bit of what my research is in right now. It's in effects due to neutral atoms, or defects in the lattice. If you have something like polysilicon, which is divided up into all these grain boundaries, right? Where this is perfect crystal, right? This is perfect crystal with some orientation, and this is perfect crystal with some orientation. As your electron is traveling through this lattice, it's going to get scattered at these grain boundaries, because of all these discontinuities. They say, one of the theories is that neutral atoms, these grain boundaries tend to be a sink for these neutral atoms, and so it's just a theory, and that's where some of the scattering takes place. But the ones we're going to talk about today are phonon scattering and ionized impurity scattering, because that's going to be the most prevalent in semiconductors, especially in silicon and germanium, right? So, let's erase that, save room. Let's start with ionized impurity atoms, right? Here. I'm sorry, we're going to start with phonon scattering, right? Phonon scattering, right? So you consider a one-dimensional lattice, right? These are our atoms, right? Silicon, something, right? And these little springy type things right here are what we can be considered as the covalent bonds in between each silicon atom. The sp3 hybridized orbitals, if that's what we call them. And each one of these behaves similar to a spring. It has some spring constant beta, and follows Hooke's law, right? And when you apply any kind of thermal energy to the lattice, these, what's going to happen is these will start vibrating. Maybe longitudinally, maybe in different directions and stuff, and what happens is, as with all this vibration, as an electron is coming by, electrons will interact with these vibrations, which we call phonons, and there will be scattering, right? So you think about it. Well, how do you increase the energy of these, of this springiness? These phonons that we call them. You increase the temperature, right? And so as you increase the temperature, naturally, your mobility will go down, right? Because there's going to be larger scattering and a greater effect on the electron drifting through the lattice, right? So here's mobility and here's temperature, right? So temperature is what we're going to focus on today here. So there are three types of phonon scattering. There's more than that, but what we're talking about is there's optical, there's acoustical, and there's polar optical. And you can actually, if you use Hooke's law and you use a Taylor series approximation, you can derive an expression for the displacement that these bonds are moving up and down. And it's something like mu sub d equals a. A is some quantum mechanic constant. I omega t, e to the I n k a, something like that, and you've got some quantum mechanical number here, and you've got a frequency. Frequency is the speed at which these things are vibrating, and a is your lattice constant. It looks similar to like this. Well, because of this, if we derive an expression for omega, And we know that energy is equal to omega times Planck's constant, right? We can actually derive a band diagram for this, and it looks something like this. We combine this to the first Brownian zone, just as before. And it looks something like this. We have two bands. One is the acoustic band. We call it acoustic simply because it's lower in frequency, right? You know, frequency is proportional to energy, right? We call this the optical band simply because it is higher in energy. It has really nothing to do with optics, right? If we have a compound semiconductor, these will not intersect at the zone boundary. They will actually, you know, the optical band will be higher up, and the acoustical band will be down here. And if you plotted your energy band diagram of the crystal structure and the momentum of the electron, you know, it actually would go up here like this, because you know it's got that Gaussian curve. It's very high with respect to this, you know. So for the acoustic band, when electrons go through the lattice, for the acoustic band, the atoms move back and forth transversely. They move back and forth in phase with each other. So if you think of like, here's one plane of the lattice, here's another plane, you know, they go back and forth, just like that, you know, in phase with each other. Right. Whereas with optical scattering, you know, which occurs at higher energy, they move opposite to each other. And so think of it like this: here's two atoms in one plane, and another is these ones will kind of scrunch in, and these ones will pull out, and it'll go, you know, the top will go out and the bottom will go in. The top will go out and the bottom will go in, and that leads to what we call the optical scattering, right? And that's, you know, this is just kind of, you know, theory stuff. You know, there's a lot more math behind this, and maybe sometime we can go through the derivation through this. But for now, I want to keep this relatively simple, and we can generalize this mobility due to optical scattering. I mean, to phonon scattering, to be proportional to m star, effective mass m star, to the negative 5 over 2 times temperature to the negative 3 over 2. And this would be for the acoustical phonon. And for the optical phonon, you know, we would have something like this, where it's m star to the negative 5 over 2, T to the negative 1. This is the temperature of the electron, by the way, times some exponential e to the h bar omega optical. You know, that's the frequency of this optical band over KTL. This T is the temperature of the lattice, right? Boltzmann constant times the temperature of the lattice. And you can see this equation actually comes from the Fermi function, except this is a Fermi function for boson, or for phonons, you know, because phonons can have quantum mechanical particle-like property, just like electrons. You know, electrons are treated as fermions, but bosons are actually treated. Phonons are treated as something called bosons. You know, and it really, you know, in terms of solid-state physics, the difference between a fermion and a boson is a fermion can only a spin up and down can occupy one state, whereas a phonon, you can have multiple phonons can occupy one state, you know, and that's really the only difference between the two. So yeah, this is I'll rewrite this up here. So the general term for mu, a phonon, is proportional to m star to the negative 5 over 2 times temperature to the negative 3 over 2, right? And that's temperature of the electron in this case, right? So that tells us that, you know, as temperature increases, right, as temperature increases, our mobility decreases, right? Just like that, right? Okay, so that's for phonon. So how about ionized impurities? So, scattering. So, yeah, what happens here? So we've got you dope a semiconductor with some donor, right? Some donor ND. Maybe it's arsenic. Some arsenic. So inside the silicon lattice, there are all these arsenic atoms, right? Maybe one in a couple billion or something, right? And you assume ionization, so at least some ionization. So this arsenic is actually positively charged. It's an ion, right? And let me just stop it. It's in the lattice, connected to these electrons, or connected to these silicon atoms. But what happens as an electron is whizzing by with some velocity vx, right? Well, what happens is it sees this this positive charge right here, and it begins to bend, right? This is some distance, delta, right? And it will bend just like this, right? With some angle theta, just like that, right? So then what, right? Well, what's the value of this angle? We find it to be, after doing some derivations, it's tan theta over 2 equals the potential energy of the electron over the kinetic energy, right? Which is equal to charge squared over 4 pi little e, which is your permittivity constant, times delta, which is the distance between the positive charged ion and the electron as it goes by right over it, times m star, the mass, times that velocity, the initial velocity that's going there, right? Well, this change in angle, represents scattering, because, right, the shortest distance between 2 points is a straight line, right? Well, you're no longer in a straight line up here. Maybe it'll straighten out as it comes back up here, but you do lose some time when you go down this distance right here, and that leads to a lower relaxation time, right? Well, so really the biggest thing that's, cations are always going to have the same positive charge, this 1 plus, this plus right here is just positive 1.6 e to the negative 19 coulombs, and this electron is always going to be negative 1.6 e to the negative 19 coulombs. So what can we really change here? We can change this delta, right, in order to reduce the scattering. But we can't go in there, and look at this lattice and find out where these, where these ions are and find out what distance these are coming by at. You can't, see that. There's no microscope in the world that can see that at that kind of speed either, But what do we do know? Well, how do we lower the probability, or how do we lower this number, right? Well, lower doping, right? So if the doping is lower, then the chances of an electron coming close to this positively charged ion become less and less, right? So as we decrease doping, we increase this ionized impurity scattering, right? The other thing we can do is if the temperature of the electron is very high, it has more energy, right? And so if it has more energy, then this angle will get smaller and smaller, because this higher energy electron will have, the effect of this positively charged ion will have less of an effect on this electron if the electron has way higher energy than the ion, right? And how do these electrons get energy? It's through temperature, right? So you can think conceptually, for an electron moving through a lattice, the mobility due to ionized impurity scattering is like this, right? So as temperature increases, our mobility increases, right? As the temperature goes up, this angle gets smaller and smaller and smaller, because the higher energy electron, due to the increased temperature, is going to have is going to be affected less by this positively charged ion, right? So you can increase the temperature and you can decrease the doping if you want to increase this ionized impurity mobility, right? Put this I, and we'll put this right here, mu phonon. Okay, all right. Well, you kind of got two scattering mechanisms that work oppositely with respect to temperature. So let's plot them both and see what we come up with. Right? By the way, for ionized impurities, let's see here, mu of ionized impurities, if we just consider this one, it's 1 over the doping ND times m star to the 1/2, right, times T, temperature of the electron, to the 3 over 2, right? And so that gives us this curve like this right here. It's temperature, and that's mu of ionized impurity, right? So let's superimpose these two graphs. Oh, and by the way, this is for if this is for a acoustical phonon, the optical phonon would be slightly under it, and if it were a polar optical phonon, it would be just a mobility actually be just a little bit smaller than that. But you know, in silicon, this acoustic phonon is going to kind of be the dominant term that we're going to look at, right? And optical too. So if we have, you know, here's mu of acoustic phonon, right? Here's mu of optical phonon, right? And here is mu of ionized impurity atoms, right? Temperature mu. So our mobility turns out to look something like this. So it rises. Our mobility rises a little bit due to ionized impurity scattering, but then at some temperature T, you know, it starts to T prime, we'll call it, starts to fall back down again due to the phonon scattering. You know, because you know the phonons are just going to keep vibrating. You know, more and more. The phonons will get higher energy. You know, as the lattice vibrates more and more, and it's going to have a stronger and stronger effect on the movement of the electron through the lattice, right? And so we find out that mu is actually, if we consider an electron, is just it's 1 over mu ionized impurity plus 1 over mu of phonon, you know, it's optical phonon, just like that. Think of it as a bunch of capacitors wired up in parallel, if you're an electrical engineer, you know. But this is the relationship of mobility versus temperature, you know. And if you wanted to find mobility of some doped semiconductor, and you knew what the doping was, you know, maybe you find it from running CV curves. Well, what you could do is, they have all these graphs in these books that were probably created by Bell Labs back in the 1950s, I think, and they are basically doping versus mobility. You know, this could be ND or NA, and they look something like this, right? Or this could be electron mobility, and this could be hole mobility, right? And hole mobility is generally less than electron mobility. You know, I think for silicon, you know, if you're doped like 10 to the 17, it's, you know, maybe something like 1500. You know, and mu, by the way, the units for mu are volts per make sure that's right. Oh, so sorry, centimeter squared per volts second. That's the units for it, right? And you can easily check, you know, V of D equal to, you know, mu times E. You know, you can easily, you know, find units for electric field. You know, well, it's like volts per centimeter, right? Times mobility, which is centimeters squared per volt seconds. You know, then you have